In this video, we're going to start the discussion of our third and final reaction type that happens in aqueous solutions, and those are reduction-oxidation reactions, often referred to as redox. This topic itself will be separated into 3 separate videos to allow you guys to focus on the ideas one part at a time. In this video, we're going to focus primarily on the introduction ideas of what redox reactions actually are. We're going to start with the discussion of what is redox in general. We'll then compare and contrast the idea of oxidation versus reduction and how to identify the two of those different elements. And last but not least, we'll talk about oxidation agents and reduction agents. And again, we'll have some examples on how to make some identifications. Before we actually get started, I have a quick example of what it means to be a redox reaction. I think this is something we've all seen before. An apple that's cut open and left on the counter will naturally start browning like this. That browning process is a reduction-oxidation reaction involving oxygen interacting with an enzyme within the apple known as phenolase. The phenolase then interacts with phenols, a chemical compound found in apples that gives them the aromatic smell that they have, and it converts those phenols into another chemical compound known as melanin, similar to the chemical compound we find in our skin, which causes skin pigmentation. Again, the compound, the phenol to melanin, involves some reduction-oxidation reactions to convert your elements from one to another, and we get a new chemical product. So let's start with the definition of what a reduction-oxidation reaction is, and these are reactions that involve the exchange of electrons, and that's the key point right here, between atoms, as well as the breaking and forming of chemical bonds. So we have chemical bonds breaking and forming just like in other reactions, but now electrons are being shared. What this causes in a lot of atoms is a change in charge. The atom that loses electrons is going to go up in charge. It's going to become more positive. The atom that gains electrons is going to go down in charge. It's going to become more negative. These commonly occur between elements and ions. The elements will gain or lose electrons, and they will give them to the ions, and then typically what was your element, has a charge of 0, becomes the ion. What was your ion, which had a charge, typically turns back into an element. The reactions that these go along with it from earlier in the year are 3 of them. We're going to focus primarily on this first one right here, which are single replacement reactions. But redox reactions also definitely happen in combustion, and occasionally they occur in synthesis reactions as well. So these are the places we can see this. Over here, something you might have learned back when you were younger, this fire triangle here. For fire to burn, you need 3 sources. You need the fuel, you need the oxygen, and you need to heat. It's the fuel and the oxygen part that undergo the redox reaction. And in fact, the word oxidation comes from the addition of oxygen atoms to the fuel, in which case the fuel is then oxidized. So let's get a little more detail here and start with a comparison of what it means for something to be oxidized versus something to be reduced. In oxidation, and these are very important definitions, we're going to be using these a lot, the element loses electrons. So the element that's oxidized is the one that loses electrons, and as I mentioned before, there is an increase in charge as a result of that. It'll become more positive. Later on, we'll talk about this topic. It'll also be an increase in what we know as an oxidation number. Reduction then is then the opposite. These are atoms that gain electrons in the process, which causes a decrease in their charge, and those guys become more negative. And you always have to have both of these. So you always have both. If you consider our ideas of conservation of matter, we can't have something losing an electron without something else necessarily gaining one in the process. A quick way to remember this is an old trick that we've been using in chemistry for a long time, and this is the phrase over here. Leo the lion says grr. Leo, standing for losing electrons, means oxidation, and grr, meaning gaining electrons, means reduction. A very simple trick you can use to make sure that you keep oxidation and reduction separate from one another. So let's take a look at a quick example here. Now, we haven't really talked a lot about how to determine the charges that these guys have, so I picked some easy reactions that kind of are grounded in what you guys have already dealt with. Elements always have a charge of 0. Copper in this case has a charge of +2 because the chlorines are -1. The iron in the end of the reaction has a charge of +3 because again the chlorines are -1. and our copper ends up with a charge of 0. What we're looking for here is the idea of what has gained and what has lost electrons in the hope of being able to identify what elements have been oxidized and what elements have been reduced. So we can see here that the iron goes from a charge of 0 to a charge of positive 3. This means the iron has lost electrons, it has increased its charge, and as you recall from before, elements that lose electrons are oxidized. So we've identified in this chemical reaction that the element iron has been oxidized. Moving on then, the copper we see goes from a positive 2 all the way to a charge of 0. This guy has gained electrons, which means its charge has gone down, which means that this element has been reduced. So the copper in this reaction is the reduction part of the reaction. So iron has been oxidized, copper has been reduced. And again, to figure this out, we identified charges. We saw how the charges changed before and after the reaction, and we tag that along back with our original description of what it means to be oxidized and what it means to be reduced. We can try this with a second reaction. We start with sodium metal. All elements always have a charge of 0. Chlorine gas, charge of 0. We end up with sodium chloride with a charge of +1 and -1. Again, the sodium has gone from 0 to +1, meaning it has been oxidized. The charge has gone up. Chlorine has gone from 0 over to -1, meaning it has been reduced. The charge has gone down, the chlorine gained electrons, and that attaches to our reduction definition. So being able to identify atoms as being reduced or oxidized is the first big step in working with reduction-oxidation reactions. So before we wrap things up, the last thing I want to talk about is the idea of not just what's being oxidized or reduced, but what are known as agents. Unfortunately, this is it's not a difficult topic, but it's something I think that adds a lot of confusion into something that's already a difficult idea. An agent is the chemical that causes a particular change to occur. So that's the key point here. It causes the particular change. Just like a real estate agent causes a house to be sold, a chemical agent or reduction or oxidation agent causes reduction or oxidation to happen. So the oxidizing agent then is the chemical that causes another substance, and that's the key here to be key thing to be watching out for. It's the thing that causes another substance to be oxidized. The oxidizing agent is itself reduced. Likewise, the reducing agent is the substance that causes, or is the element that causes another substance to be reduced, and it is itself oxidized. And these guys, again, are very closely related to one another. And the thing you can think of is something that is more easily reduced makes a better oxidizing agent. So if your substance here is more easily reduced, it is a better oxidizing agent. It is better at making that reaction happen faster. And likewise, the reverse is obvious here. Something that is more easily oxidized is a better reducing agent. It's better at making the other reaction happen faster. We're going to talk about whether things are easily or more difficultly reduced or oxidized in a later video, but this is just an idea to keep in the back of your head. So to wrap up, we can get one last example. Again, to identify what's being oxidized or reduced, we need to look at charges. Elements always have a charge of 0. Hydrogen's +1, chlorine's -1, aluminum's +3, chlorine -1. In this case, hydrogen ends up being 0. If identifying these charges is not super obvious, we do have another video later in the path that'll talk more about this process. But really, we're just focusing on charges and ionic compounds from earlier in the year. Anyway, we can see here that the aluminum is going from aluminum 0 to aluminum +3, meaning it is being oxidized. But more importantly, according to what we're dealing with now, that means aluminum is your reducing agent. So we can be able to identify that as our reducing agent. And likewise, hydrogen is going from +1 down to a 0 charge. Its charge is decreasing, meaning it is being reduced. But that also means it is the oxidizing agent. So this is the second thing I expect you guys to be able to identify here is not only what is being oxidized or reduced, but also what the oxidizing agent and the reduction agent are. Again, it might seem like an unnecessarily complication, but later on down the road, being able to identify these is going to help us in our discussion of reducing and oxidizing reactions. So that's pretty much it. Quick video. You should be able at this point to describe what a redox reaction is, the idea of an exchange of electrons. You should know what types of reactions are typically associated with redox. We said primarily single replacement, but also combustion and synthesis reactions. You should be able to identify which elements are being oxidized or which are being reduced by looking at charges, and then later things we'll call oxidation states. And then last but not least, you should be able to identify the oxidizing and reducing agents. If you know what is being oxidized and reduced, the oxidizing agents are just those same things, but reversed. As I said, this is an idea that's going to develop further. We have other videos that are going to talk about some of the more details. And eventually, all of this leads up to the ability to balance an oxidation-reduction reaction.